Mattson. Welcome to Physics 150, College Physics 2, and I like to call it Electric Boogaloo because we're going to be looking a lot at electricity in the first part of this semester. My name is Mark Mattson. I'm an associate professor in the Department of Physics and Astronomy here at JMU. I'm teaching two sections of this course. One is going to be online throughout the entirety of the semester. That's Section 5. Section 2, the intention is that we will be meeting face-to-face if or when that is allowed, and that will be in NGO 1210. But for the time being, we are going to be strictly online. So let's discuss the course and what you can expect, and we're going to start by discussing what's on the syllabus. Now, I'll show you the syllabus, but here are the highlights. Over the course of the semester itself, there are going to be 3 tests, and of those 3 tests, the top 2 scores will contribute towards your final grade. There will also be a final exam that will count towards your final grade. You can't replace the final exam with one of the 3 tests from the semester. You have to take the final exam. The tests and the exam, I'm going to administer them online. I'm administering them online because I want to be in a position where I can convert quickly to an entirely online format if the pandemic doesn't get any better. So the exams and the final exam, whether you are in the in-person section or the online section, they will be conducted online. In fact, they will be conducted online on the LON-CAPA system. Those of you who had me in the Physics 140 should be familiar with LON-CAPA. I imagine that others are also familiar with LON-CAPA, but I will discuss it a little bit here. LON-CAPA is a system that is separate from Canvas. It's in some ways nicer to work with than Canvas because there's more flexibility in developing problems and administering them in a way that they're randomized for everybody. We'll be using LON-CAPA not just for the exams, but there will be reading quizzes that will happen most days, and there are going to be homework assignments most weeks. So let me show you a little bit about LON-CAPA. I'm going to exit out of the PowerPoint here, and let me just log out of this. I'm going to log in again. And you'll log in using your regular JMU user ID password combo. Your username should be all lowercase and do not capitalize any letters. Your password is exactly what it is for JMU. So, assuming I remember it correctly. And when you log in, you will see a list of courses. Now, I have a lot of courses because I've been using LON-CAPA over many years. You'll see a few courses, and among the courses should be a course for Physics 150, either Section 2 or Section 5. And whichever one you pick, or whichever section you're in, you should be able to see it. You will select it, and you'll be taken to this page here, and you can click on Contents. I have a lot more things to click on here than you'll see, but you should see a link for Contents. And if you click on Contents at this point in time, you will see something for reading quizzes, and you will see something for homework assignments. The reading quizzes, if you pop that open, you'll see that I have a reading quiz that is actually ready for this coming Friday. And the reading quiz, you click on that, it'll pop open here, and then you can start clicking on the problems. And all of the reading quiz questions are strictly multiple choice. The exams will be multiple choice as well. The homework assignments, though, will involve entering answers. But here's an example of a reading quiz question, which of the following best describes the relationship between the force one charge exerts on another and the separation between them? I will give you a hint, in fact, more than a hint, for this question right here. The force is inversely proportional to the square of the separation between the charges is the correct answer. However, when you submit that answer, you will not be told whether or not that answer is correct. Now, this answer is correct, I know, but you're not going to be told whether or not it's correct until after this reading quiz is due. When is this reading quiz due? And you can see that it is due this Friday, January 22nd. If you're in Section 2, it's due at 10 a.m. And if you're in Section 5, it will be due at 11:15 a.m. In either class, it's due a half hour before class begins. Reading quiz questions will be due a half hour before class begins. And you should always assume there will be a reading quiz for any given day. The only guaranteed exceptions are days on which we have an exam. If we have an exam scheduled for a particular day, we will definitely not have a reading quiz on that day. But any other day, you should assume that there is a reading quiz. And you will come here to Lon Kappa, check your reading quiz, and you'll see that there is a reading quiz for January 22nd, 2021. Currently, you will not be able to see the reading quiz for January 25th, Monday, January 25th, but I will open that up after Friday's class. All reading quiz questions should be available at least 24 hours prior to their due date. If there is not going to be a reading quiz question and it is intentional on my part, I will announce it on Canvas. And I'll show you where I'll announce it on Canvas when we get there, but while we're still in Lon Kappa, I want to show you about homework assignments. You can also pop that open. And you can see that I actually have a homework assignment due on Friday. You can assume that there will be homework assignments due on Friday, except on Fridays where we have an exam. So, you click on that. Well, first of all, before you click on that, you see one that says due 1/22/21, and you see one that says due 1/22/21-practice. Let's start with the one that says practice. Now, the question here is going to be as easy a question as you will ever encounter in any physics course, because I just want to make sure that you are able to log into Lon Kappa. And the question is just going to be adding two numbers together. What's 8 plus 5? Now, of course, the answer is 13, but let's say, oops, I put in 11 and I submit the answer. Oh, the practice question tells me that I got it incorrect. Oh, well, that was kind of dumb. I meant to type in 12, a derp. Oh, still incorrect. Well, let me just keep trying. Let's try 13. Oh, hey, yay me, I got it. Okay. So presumably, now you know how to do this problem. If you figure out how to do the practice question, that will tell you how to do the question that is not labeled practice. Here's the key. The question that is not labeled practice will count towards your grade. This question right here will count towards your grade. What's 10 plus 10? Of course, we all know the answer is 19, right? And this is just going to say your answer is submitted. This is the problem that's going to be graded. Now, you can always go back and say, wait, that's not the answer. Obviously, it's 20. And you submit the answer, and that's the answer that's going to be graded, unless you come along and put in a different answer. Whatever the last answer you submit is before the deadline, that's the answer that's going to be graded. So once you figure out how to do a problem correctly in the practice, you would have to go back to the set that is labeled not labeled practice and do those problems. Those are the problems that count towards your grade. The problems that are labeled practice do not count towards your grade. And please don't ask me to make them count towards your grade. I never have, I never will. You're supposed to do the problems that don't count towards your grade. You're supposed to do the problems that aren't labeled practice because they do count towards your grade. So, recapping, do 122.21 practice does not count towards your grade. Do 122.21 does count towards your grade. Let me know if you have questions about that. You can also see on Lawn Kappa that I have a link that is hidden from you, which will be where I place the tests. When the tests are ready to be deployed, you'll go onto Lawn Kappa, you'll see a link for tests, you'll click on it, and when the tests are there, you'll see the link for them. Now let's go to the Canvas webpage. On the Canvas webpage, you see the syllabus, you see the bureaucratic stuff, you see my name and contact info. I suggest using email. And I might point out that my last name is Mattson, M-A-T-T-S-O-N, and my email is Mattson, M-A-T-T-S-O-N-E. Please distinguish between the two. My last name is not Mattson, my last name is Mattson. So pet peeve, it's generally a good idea to get people's names correct. That's all I'm saying. You can see my office hours, and the text is this online text via OpenStack. The link is provided. College physics, and you probably saw this in Physics 140. We'll be using this text once again for Physics 150, excuse me. The breakdown of the grades. The reading quizzes will account for 10% of your final grade. Of the 3 exams taken during the semester, the top 2 count. Each of them is 20% for a total of 40%. The final exam is 25%, and the homework assignments are also count 25% towards your grade. Get in the habit of doing these things. I've seen many students who slack off on doing the reading quizzes. If you don't do the reading quizzes, you're basically lowering your potential final grade by a full letter grade. So don't forget the reading quizzes. There's some material on if you are unable to take an exam or a reading quiz. Documentation should be provided where it's applicable. University sanctioned event or religious observance that you know about in advance, you should let me know in advance. If it's a sudden personal situation, notify me as you can. I mean, don't remove your hand from the tourniquet so that you can text me, but let me know when you can. I am not going to be taking attendance, but if you are not coming to class and paying attention, you're doing it wrong, and your grade will suffer. You really ought to come to class regularly, basically all the time, and just be diligent about it. Now, how am I going to run this class? Those of you who have me in Physics 140, the format is basically the same. So maybe you can tune me out for a couple of minutes if you haven't already. What do I expect? Prior to the next day's class, let's take a look. If you click on Modules on Canvas, you'll see I have a lecture for 120.21. And if you click on that, you'll see I have some PowerPoint slides, and I have an equivalent set of PDFs and recorded lecture. The recording that I'm making right now, I will post here when it's ready. And you can see the PowerPoint slides and you can see the PDF slides. Now, this day is an exception because it's the first day. Let's take a look at Friday's lecture. A lecture for January 22nd, 2021. You'll see I have a reading assignment. You'll see that I've already posted PPT slides, PowerPoint slides. You'll see that I've posted PDF slides. I will make a recording after Wednesday's class with narration of these PowerPoint slides here. I'll make that recording. I will post it here. The expectation is that prior to Friday's class, you do the reading from the textbook. You at least view the PowerPoint slides, if not actually listen to my narration. Like I said, the narration will come after Wednesday's class. That will be posted. Then in Friday, I'll have a different set of slides for the in-class lecture. And we will go through these slides. The slides will augment the pre-class slides that I expect you to view. They'll have examples, they'll have some discussions, they'll have opportunities for you to practice. After class, I will post these in-class PowerPoint slides. I won't post them before class because many times I'm modifying them up until class begins. So they will not get posted until after class. I will post the PowerPoint version of the file. I will post the PDF version of the same slides. Also, I will record the lecture on Friday. The lecture on Friday the recording will then be posted here after class on Friday. Speaking of lecture, in these first couple of weeks, you will be able to access class via clicking on WebEx. I will set up these events as the time comes so that you will see, for instance, lecture starting on Friday, January 22nd. You'll be able to click on the link, open up the meeting, and you will be automatically placed into the meeting. So, let's recap. Lon Kappa for reading quizzes, which are going to be nearly every class period. Lon Kappa for homework assignments, which are going to be nearly every week. Lon Kappa for all the tests. Make sure you can log into Lon Kappa. Let me know if you are having problems. Send me screenshots so that I can see what's happening. I might be able to identify what the problem is from the screenshots. The lectures themselves, reminder, they are available under modules. You will see the different lectures over time. This is going to pile up, and we will just see a long list of lectures as we progress through the semester. For the lectures, there will be material that I expect you to view prior to coming to class. The reading quizzes are based on those materials, so you have to view the materials and read the textbook in order to have your best shot at the reading quizzes. You view those materials. You come to class, you get more slides, and after class, those slides and the recorded lecture will be posted, as you can see in the spots here. Now, I hope it's all clear. Let's take a look at the schedule that I've developed for the semester. And we see our introduction starting today, and we have some material that I will discuss with you, and we'll have these. You'll see more specific reading assignments. This is what you see here on the syllabus is a tentative schedule. Frankly, I don't think we're going to go this fast, and I don't have any problems with it. You can see the first exam is scheduled for February 12th, and if we were to stick to this plan, it looks like that there would be some material from Chapter 21 on exam number 1. It might be we go slower than this schedule. And maybe prior to the first exam, we don't get to Chapter 21. If we don't cover that material prior to the exam, that material will not be on the exam. As we get close to an exam, I'll try to be specific about where the material ends so that you can focus on what you need to study for the exam. The final exams are scheduled for May 3rd, whether you're in Section 2 or Section 5. But again, they're going to be administered online, and I will, as we go along, it'll make more sense when I say that. I'll set up a window of opportunity for you to take the tests, and it won't necessarily have to be from 8 a.m. to 10 a.m. or 10:30 a.m. to 12:30 p.m. It will certainly encompass those times, but it won't necessarily be limited to those times. We'll figure out what that means when we get to the first exam. Some other pieces of information you might want to take a look at in the syllabus. Don't forget the honor code. I do believe in that. And I hope that kind of gets you started for the material for the semester and gives you an idea for what to expect. What I would like to do now is start discussing some of the actual physics. So without further ado, why don't we do that? And as I intimated at the start of this lecture, there's going to be a focus on electricity. And just a very brief historical overview, anybody who's ever seen lightning has seen electricity. So observations of electricity go back at least that far when our hominid ancestors heard thunder and saw lightning and were undoubtedly frightened by the sight and sound. There was also the observation of static electricity. There is a crystalline material called amber, basically fossilized sap, and it does have some static electrical properties. And in the 1600s, the scientists of the time realized that it seemed like there were two different kinds of charge. And in the 1700s, it was none other than Benjamin Franklin who said, hey, let's call this type of charge positive and this type of charge negative. The idea of electric charge, first of all, like I said, it could be either positive or negative. When you look at most objects, it seems like that the total electric charge is zero. You don't get any static effects from it. It's only a few objects that seem to get static effects, and they mostly seem like, socks from the dryer or something like that. But all objects, for all intents and purposes, possess electric charge. It's just that the number of positive charges tends to be very close to the number of negative charges. When we see distinctly non-zero charge, it's not because this electric charge has appeared out of thin air. It's because there's an asymmetry in the distribution of charge. So that sock, for some reason, has picked up electric charge from some other object. So one object might lose charge and the other object gains charge. And so if one object loses charge, it actually is still going to demonstrate electrical properties. By losing charge, it means it is, if it starts off electrically neutral and loses charge, it's going to become electrical. If it starts off as non-electrical but it gains charge, it's going to be electrical. So losing charge means becoming more negative in charge, and gaining charge would mean becoming more positive in charge. Either way, the further your charge deviates from zero charge, the more electrical the object becomes. What is electric charge? Hard to say, but to get a grip on what it does, we can use an analogy with mass. The gravitational force is the result of two objects with mass interacting with each other. The electrical force is similar, except that it's the result of two objects with charge interacting with each other. So what mass does for gravity, charge does for electricity. It's a property an object has. Just as an object can have a property of mass, that same object can have the property of charge. The big difference is that all mass that we see is effectively positive mass. We have never seen any such thing as negative mass. But electric charge, we see positive electric charge, we see negative electric charge, and the tendency is for most objects to have a charge close to zero, because the number of individual positive charges within it is very close to the number of individual negative charges within it. In gravity, masses always attract each other. But in electricity, it is possible for charges to attract each other, but under other circumstances, those charges will repel each other. Now, what are the circumstances? A positive charge and a negative charge attract each other. A positive charge attracts another positive charge, and a negative charge attracts another negative charge. So we see in the graphic here 3 pairs of charges, and they're fixed in place, but if I let them go, the two positive charges at the top will repel each other. The two negative charges at the bottom will repel each other. But the positive charge and the negative charge in the middle are going to approach each other. Opposite charges attract each other, like charges repel each other. If you've ever heard of the expression opposites attract, it's basically because somebody decided that what happens with electric charges and magnets, as we'll see later, applies to relationships between people, but frankly it doesn't. Now, if I have 2 opposite charges come together, do they, annihilate each other or something? No. Because consider an atom. Let's start off with the simplest atom of all, hydrogen. A hydrogen atom consists of a positively charged proton and a negatively charged electron that orbits around it. The negatively charged electrons stay close to the positively charged proton, but they don't collapse in on each other. The reason they don't collapse in on each other is because of quantum mechanical effects, which is basically the physics professor's way of saying crazy stuff that we're not going to discuss in detail right now. Quantum mechanical effects keep the electron from collapsing into the proton. And in chemistry, it is possible for a positive charge and a negative charge to exist in very close proximity to each other. You can look at the situation of an ion in sodium chloride, regular old table salt. The sodium atom by itself is neutrally charged, but if I remove an electron from it, what's left behind has a net positive charge. And if I take that electron and I add it to an otherwise neutral chlorine atom, there's now an excess of electrons, and so there is an excess negative charge on the chlorine atom. And so if we have the sodium ion, an ion means that the electric charge is non-zero, and we have the chloride ion. The sodium ion is positively charged, the chloride ion is negatively charged. The two attract each other and can assemble with other ions into a crystalline structure that is table salt. So that's a situation where they don't collapse in on each other. Another situation where we have a negative charge in close proximity to a positive charge is the electric dipole. An electric dipole is an object in which one side has a distinct negative charge and the other side has a distinct equal and opposite positive charge. And when we have such a configuration, we would say that we have a polar object, an electrically polar object. Now, a little bit about materials on a macroscopic scale. A dielectric material is a material in which the atoms can become polarized. If I take these atoms and I place them in an external electric field, that external electric field exerts a force on the atom that can twist the configuration of electrons in the atom, not carrying the electrons away from the atom, but just readjusting their locations. And so that one side of the atom will tend to have the electrons congregate a bit more frequently than the other side. Where the electrons are congregating, there's a net negative charge. Where there's a deficit of electrons, there's a net positive charge. And so a dielectric material, the atoms on their own might be very nonpolar, but you place them in that external electric field, and with the redistribution of electrons in the atom, you can induce an electrically polar situation. Now, aside from dielectrics, there are other kinds of materials, and in these broad categories, we have conductors, we have insulators, and we have semiconductors. And these labels are based upon how they respond in the presence of an external electric field. If you have a material that is a conductor, conducting materials have within them electrons that are virtually free from the atoms to which they were originally attached. For instance, copper. In copper, there tend to be one or two electrons that are only very loosely attached to the copper atom. Basically, I can take a copper atom and I can shake it, and it will shake off one or two electrons. Those one or two electrons remain within the overall copper material, but they're kind of free to move around. And when I apply an electric field, that creates a force on those electrons, and it starts pushing them in a particular direction. Materials in which we have these free electrons ready to start moving in whatever direction, those are called conductors. So when we have a motion of charge, we get an electric current. Conductors are great carriers of electric current. They carry electric current very readily. At the other extreme are insulators. The atoms within an insulator, there are no electrons that are loosely bound to the atom. All of the electrons are pretty strongly attached to the atom. And no matter how you shake it, those electrons are not going to be broken off from the atom. So you don't get this flow of electrons when you apply an electric field, even if you apply a large electric field. There's no electric current in an insulator. So in a sense, it's quite the opposite of a conductor. And when you look at wiring inside a household, you might see a metal at the core of the wire. Might be copper, might be aluminum, some other metal, but surrounding it is going to be a rubbery material, and that's an insulator. You can have current running through the metal part of the wire, but if you grab that wire by the insulating material, you're safe. You're not going to get an electric shock because the insulator will not conduct these moving charges into your fingers. In between those extremes, we have semiconductors. In most circumstances, semiconductors kind of behave like insulators. But unlike an insulator, it is possible to place a semiconductor in a strong enough electric field that electrons are stripped off of the atoms. So they don't easily give up electrons, but with enough stimulation, they will give up an electron. And so if there's a strong enough electric field, you can start getting a current through a semiconducting material. But if it's a small electric field, it's like having an insulator. This is actually a very valuable property in the electronics industry. The electronics industry is based on the binary numerical system, either 0 or 1. And you can think of 0 as, say, no current running through a particular location, and a 1 as, yes, there is current running through it. Now, you don't want a stray electric field causing a current running through a location where you don't want current. You don't want a stray electric field causing an induced current. Well, a stray electric field will not induce a current in a semiconducting material. There has to be a very conscious application of a reasonably significant electric field in order to get current running through a semiconducting material. So the fact that stray electric fields won't cause current mean that if you want to have a very particular number on your calculator, you can get it with semiconducting materials. You could not get it with conducting materials. At the elemental level, the periodic table is pretty good at telling you whether a substance is a conductor, an insulator, or a semiconductor, aka metalloid. If you look on the periodic table on the screen, you'll see kind of a thick staircase-like line. If you look to the left of that staircase-like line, you find metals. Those are conductors. If you look to the right of the staircase-like line, you find nonmetals, which are insulators. On the other hand, some of the elements that straddle the staircase are semiconductors. Silicon is a semiconducting material. Gallium and germanium and arsenic are used as semiconducting materials. Antimony is used as semiconducting material. The semiconducting materials tend to straddle this staircase-like line. The many elements to the left are metals and are conductors. The fewer elements to the right are the nonmetals. Those are the insulators, at least at the elemental level. If we start looking at molecules, well, that opens up the door to thousands of different materials, and I don't want to go into that. So, I talked about a force between charges. Let's look at the equation. And having already pointed out that there's an analogy with gravity, let's continue with it. We have Newton's universal law of gravity. That allows us to determine the force between two masses, the gravitational force. What about the electrical force between two charges? First of all, units. Mass is measured in kilograms. Electric charge is measured in units of coulombs. You can see the word spelled out, named after a French scientist, Coulomb. And kilogram is abbreviated kg. Coulomb is abbreviated as a capital C. Capital C, units of electric charge, the coulomb. Mass is represented by the symbol lowercase m. Charge is represented by the lowercase letter q. So keeping these parallels in mind, what's the equation? And, well, here's the gravitational equation. Newton's universal law of gravity. The magnitude of the gravitational force between two masses m1 and m2 is equal to capital G, which is a constant. It's a constant that represents the strength of the gravitational force in our universe. The universal gravitational constant, capital G, times the mass of the first object, m1, times the mass of the second object, m2, divided by s squared. S is the separation between the two masses. Don't forget to square it. Okay, yeah. That's gravity. But I wanted to remind you of this equation, because the equation for electricity is remarkably similar. the magnitude of the electrical force is equal to a constant. This constant represents the strength of the electrical force in our universe. It is called the electrostatic constant of the universe. So, represented by a lowercase k, the electrostatic constant of the universe, times the charge of the first thing, times the charge of the second thing, divided by the square of the separation between them. You might remember that reading quiz question that I mentioned, that the force is inversely proportional to the square of the separation between the charges. That's what's being discussed here. The parallels between the equation for gravity and the equation for electricity, I think, are pretty obvious. But let's make sure we understand. I talk about the electrical force, but it's a force. And a force is a force, of course. It's measured in newtons. It is a push or a pull, just like any other force. Q1 and Q2 are the electric charges measured in coulombs as the standard unit. But bear in mind, 1 coulomb is a heck of a lot of charge. I mean, it is a lot of charge. You'll typically see measurements of microcoulombs, nanocoulombs, picocoulombs. You'll have to get used to those metric prefixes when we start dealing with typically encountered amounts of electric charge. As, of course, at the separation, you use the standard unit of meters. K, as I pointed out, is the electrostatic constant of the universe, and it's equal to 8.99 times 10 to the 9 in standard units. Well, you see newtons times meters squared over coulombs squared. That means in standard units. If your charges are in standard units and your separation is in standard units, then K is 8.99 times 10 to the 9. Recalling that Q1 and Q2 could be positive or they could be negative. If you multiply the two together, you might find that the force is a negative quantity. If you multiply the two together, you might find that the force is a positive quantity. Well, the interpretation is that if you get a negative value for the force, it means that the force is attractive. And if you get a positive value, the force is repulsive. But you already should know that. If the charges are opposite, it's attractive. If the charges are like, it's repulsive. So don't worry about that too much. The magnitude will be whatever the absolute value is, and then you can just look at the charges and say whether the force is attractive or repulsive. Let's take a look at an example. What is the force between two charges, negative 6.28 microcoulombs and 75.4 nanocoulombs, separated by 8.91 centimeters? Now, none of these are given in standard units. All of them have metric prefixes that we need to take into consideration. Micro means times 10 to the negative 6. So we'll say Q1 is equal to negative 6.28 times 10 to the negative 6 coulombs. Nano means times 10 to the negative 9. We'll say Q2 is 75.4 times 10 to the negative 9 coulombs. And of course, centimeters, when we convert centimeters to meters, we move that decimal point over a couple of places, and we get that it's 0.0891 meters. And now we can plug into Coulomb's law. 8.99 times 10 to the 9 times negative 6.28 times 10 to the negative 6 times 75.4 times 10 to the negative 9 divided by 0.0891 squared. And you combine all those, and hopefully you'll agree with me that you get negative 0.536 newtons. Now, the negative sign, like I said, it's just kind of an indication of whether the force is attractive or repulsive, but we already know. It's a negative charge and a positive charge. The force is attractive. That's all it means. But I do want to point out, we're talking about a force with a magnitude of about half a newton. If somebody pushed on you with a force of half a newton, you'd feel it. Note that we're talking about pretty small charges. 10 to the negative 6 coulombs, 10 to the negative 9 coulombs. And yet we get a fairly appreciable force out of those tiny charges. The electrical force can be surprisingly strong. Why? Well, ultimately the reason why is we don't know, but it manifests itself when we look at the electrostatic constant of the universe and compare it to the gravitational constant of the universe. The electrostatic constant of the universe is 8.99 times 10 to the plus 9. The gravitational constant of the universe is 6.67 times 10 to the negative 11. That's a difference of 20 orders of magnitude. So the raw numbers for the strength of the electrical force in the universe compared to the strength of the gravitational force of the universe, the electrical force is stronger by a factor of 100 quintillion. But of course, because there are both positive charges and negative charges, the net charge of objects tends to be very close to zero. Whereas, if I start combining masses together, I always have positive mass. And so the more masses I have, the more total mass, the more non-zero, the further away from zero the mass gets. I can't say the same thing about charges. But if you've ever thought about static plane, you pull a sweater out of the dryer and there's a sock stuck to it. Now think about it. The entire mass of the Earth is trying to pull that sock down, and yet that stupid bit of static electricity is basically telling the Earth to take a hike. That stupid bit of static electricity can be substantially stronger than the gravitational force. It's rare for there to be a noticeable departure from zero net charge, but when there is, the effect is substantial. When we look at things, the total charge tends to be very close to zero. Why is that? It's happening at the atomic scale. When we get a non-zero charge, most of them are because of a change in the distribution of electrons. Electrons have a negative charge. The charge of an electron is negative 1.602 times 10 to the negative 19 coulombs. That happens to be equal in magnitude but opposite in sign to the charge of a proton, positive 1.602 times 10 to the negative 19 coulombs. So if I get an electron close to a proton, the net charge of that system is zero. When there is non-zero charge, macroscopically on an everyday scale on an object, it's likely that electrons have been either added or removed from it. If electrons have been added to it, the object has a net negative charge. If electrons have been removed from it, the object has a net positive charge. We can very rapidly get significant static effects, but we don't get significant gravitational effects. Not only is capital G way less than K, but a difference in the number of electrons has a relatively significant impact on the total charge and extremely little impact on the total mass. If, once again, we look at the raw numbers, the charge of an electron, the raw number associated with it, has a magnitude of 1.6 times 10 to the negative 19. Whereas if we look at just the raw number associated with the mass of an electron, we get 9.11 times 10 to the negative 31. On our scale, both of those are ridiculously small numbers. But on their scale, the number associated with the charge is 100 billion times greater than the number associated with the mass. So a change of one electron has a more significant electrical effect than gravitational effect. Let's take a look at this example. We have a sphere made out of conducting material, and it starts off neutral. And it has a mass of 5.53 grams. Suppose it gains 4.21 times 10 to the 15 electrons. That's 4.21 quadrillion electrons. What is the new charge of this sphere, and by how much does the mass change? All electrons have a charge of negative 1.602 times 10 to the negative 19 coulombs. So if I have 4.21 quadrillion electrons, the total charge of all of them is 4.21 times 10 to the 15 times negative 1.602 times 10 to the negative 19. And I calculated that to be negative 6.75 times 10 to the negative 4 coulombs, which is equivalent to negative 675 microcoulombs. That is actually a pretty good amount of electric charge. On the other hand, what about the mass? Each electron has a mass of 9.109 times 10 to the negative 31 kilograms. If I have 4.21 quadrillion of them, then that winds up being equal to 3.84 times 10 to the negative 15 kilograms, which is nothing. You simply cannot detect the effect of 3.84 times 10 to the negative 15 kilograms. I just want to mention what happens when two objects come into contact with each other, and I want to look at the situation of conducting spheres. Conducting spheres allow for the most rapid transfer of charges. We can get a transfer of charges even if the materials aren't perfectly conducting, but I don't want to complicate things. If we let two conducting spheres come into contact with each other, if one of them has non-zero charge, then when they come into contact, because the spheres are made of conducting materials, charge can transfer from one sphere to another sphere. If one sphere starts off positive and the other starts off neutral, and they are allowed to come into physical contact with each other, some of the positive charge on the first sphere will be placed on the second sphere. The charge on the first sphere will drop, but it will be compensated for by charge on the second sphere increasing. The total charge on the two spheres added together will be equal to the total charge that was just on the first sphere before they came into contact. Same thing would happen if one was negatively charged and the other is neutral. They come into contact, both of them now have a negative electric charge. If they both have charges, and it gets a bit more complicated, unless the spheres are identical in shape and size. If they're identical in shape and size, then what will happen is the amount of charge on both spheres after contact will be equal. And the sum of those charges will be equal to the sum of the charges before contact. Electric charge is a conserved quantity. We don't get electric charge appearing out of thin air. We don't get electric charge vanishing into thin air. It's all accounted for. It is a conserved quantity. So let's say we have two identical conducting spheres that come into contact. One starts off with a charge of negative 47.3 microcoulombs. But after contact, that same sphere now has a charge of positive 13.5 microcoulombs. How much charge was initially on the second sphere? Well, the trick is recognizing that after contact, because they are identical, both spheres will have the same charge after contact. So if one of the spheres after contact has a charge of positive 13.5 microcoulombs, the other sphere after contact will have a charge of 13.5 microcoulombs. And the total charge of both spheres after contact is positive 27 microcoulombs. That means that the total charge before contact was 27 microcoulombs. Q1 plus Q2 is always going to be equal to 27 microcoulombs. But before contact, Q1 was negative 47.3 microcoulombs. So what that means is that before contact, Q2 must have been positive 74.3 microcoulombs. Okay, that's enough for now. I hope all is well. You let me know if you have questions.